Right. So welcome again to lecture number 2, ME210 fluid mechanics. So in the previous lecture, we were talking about some basic introduction. We also talked about what fluid mechanics is and why you need to learn it. Okay, I was still working on the talking about what fluid mechanics is. So let me let me continue the discussion. So I was telling you that fluid mechanics, the word mechanics is there. So there is no new physics that you're going to learn. It is just the same Newton's second law of motion that will be applied. But of course, the complexity will increase. So we will have systems where you would want to study a particular fixed volume in space rather than talking about a particular mass that you're tracking. So earlier we used to talk about the free body diagrams of a given collection of masses or a given mass, and then say force acting on that mass equals force acting on that mass equals the mass times acceleration of that mass. But now we'll talk about some fixed volume in space. So there may be masses entering and leaving that fixed volume. There may be something interesting happening inside the fixed volume. So these things will give some level of complexity as to how to write the equations. Okay, so that is something new that we'll be learning here. And of course, since we're talking about fluid mechanics, we will definitely be analyzing the results that we get from these laws of motion in terms of the intuition and in terms of the effect it has on engineering systems. Okay. So let's talk about, so today what we'll do is we'll talk about a lot of ideas. Okay, because before we start diving deep into the equations and their analysis, let us first talk about a couple of ideas which are very important and which will be valid throughout this course. So I'll say that this lecture is about ideas. Fundamental ideas. Okay. There may be a slight lag between when I write something on my board and when you see it. It's a Jamboard session that's been shared, but there shouldn't be too much lag. Okay, so just bear with me in that. So the first idea we want to talk about is called the continuum concept. So for those who are doing a course in continuum mechanics, they may already have heard of it. But for those who have not done this course, who are not doing this course, we need to talk about it here. So this idea of continuum concept, what it says is, if you take, in reality, the matter is discrete. If you take any material, it's made up of atoms. And if you remember the chemistry from high school, you may remember that the atoms, there's lots of void space when you talk about atoms. Okay, there may be bonds between them, but otherwise there is void space. Even if you see electrons and protons and neutrons, then you will see that mostly it's empty. And then very concentrated charges are there. So matter exists in a very discrete sense, but the kind of engineering, the real systems that we consider, let's take a very small volume, a cube which is in a very small size. Let's say the size of this cube is of the order of 10 microns. So 10 microns is 1/100th of a millimeter. So 10 micrometer. So this very small cube that we have, so let me just zoom out of it. Yeah. So this very small cube that we have, let's say this cube is a hypothetical cube in air, and this cube will end up having around 10 billion molecules of air. Okay, of oxygen, carbon dioxide, and so on, nitrogen. So it will have around 10 billion molecules. So if I wanted to define, let's say, the pressure at a point, I could comfortably say that I will never go smaller than this cube. Okay, and whenever I want to define a pressure at a point, I will take a cube. Sorry, I will take a cube which is of this dimension around that point, with that point being on the center, and then I'll calculate the average pressure that is exerted by all the molecules in that cube. If you want me to calculate the temperature at a given point, I can calculate the average temperature of all the 10 billion molecules which surround that point in that cube that surrounds that point. Similarly, if you want me to calculate the velocity, that is velocity is nothing but its three components. So I will find the velocity of all the 10 billion molecules. I'll average them, and that will give me the velocity vector as an average of those 10 billion molecules around that point um, P. So then this kind of strategy, it allows us to define um, quantities at a given point in space, even though strictly that point may lie somewhere where there is no material at all. There's no electron, proton, neutron at that point. So it in all senses it's empty, but we can use the continuum concept to define quantities at points. It's a very important idea, but mostly we won't worry about it because I mean, we are not dealing with those situations where we end up going into a very small scales. So for all practical purposes, for engineers, for us, the continuum concept is always valid. Okay, so you may think in terms of molecular ideas, but don't go to the molecular scale to define things, because the continuum concept will fail. So the equations that we'll be developing in this course will fail if you go to the molecular scales. Okay, is that clear? Fine. So let's talk about the next idea for today. Okay, let's talk about what fluid mechanics has been for us. So I will I what I did was I picked up a textbook from your high school, and had a look at what fluid mechanics has been taught to us in the high school level. Okay, so it's very important to understand what is the level that we're comfortable with, and then build over that. So there's no point repeating ideas that we already know. Okay, so in the high school level, you have learned a lot of fluid statics. So you may remember the Pascal's principle. Okay, you may remember that. I mean, if you change the pressure in a fluid, it travels extremely fast. So if I change the pressure in a fluid here, I will see the change in the pressure of the fluid here if it's connected immediately. You also learned about the fact that I mean, the hydraulic jack, the idea of hydraulic jack. So you have to apply um, lesser force to be able to pick up a car, which requires a lot of force. Okay, so the idea is the idea of pressure, force per unit area. So this is something we know. You also have learned a lot about U-tubes. Okay, you have done lots and lots of problems of those U-tubes where you had to there was some fluid in the U-tube, and there's another fluid in the U-tube, so you have to find out the pressure at a given point and then equate them and so on. Okay, and you may have done very complicated problems where the tube is quite complicated and it's filled with fluid and so on. Okay, so you have done this. So this is something you're very comfortable with. Then you have learned about the Archimedes principle. Okay, that was nothing but buoyancy. You have done lots of problems of these floating wooden blocks in water or some liquid. So you know that what is the meaning of apparent weight. So if a human goes into a swimming pool you feel yourself lighter. So there is a force of buoyancy that acts opposite to the direction of gravity. And the force that is acting, the force of buoyancy, is equal to the weight of the fluid that is displaced by the body that is inside the fluid. So this is again fluid statics, and we are very comfortable with this. We have done very complicated problems in the past of you take a wooden block, you press it, it oscillates and all these things to calculate the frequency of oscillation and so on. Okay, so this is something that we're comfortable with. We also have done some dynamics. So we have learned about compressible or incompressible. I mean, the word is clear. So there's something called compressible fluid, and then you have incompressible. Sorry. So that is the density can or cannot change. So, for example, air is compressible, but water is incompressible. At least for very large pressures, water does not compress. We've talked about, you learned about the idea of viscosity. Okay, the word viscosity makes sense to you. And you also have learned of ideal fluids which are inviscid, which are not viscous. There's no viscosity in them, no friction in them. Again, we'll learn these ideas further, but I just want to talk about things we already know. Then you have learned about something called steady flow. That is, nothing changes with time. Whenever if I come after 1 hour and look at the flow, then it will look extremely similar to what it was 1 hour ago. Okay, so things are not there's nothing that is a function of time anymore. It has reached a steady state. You've learned about the word rotation or rotational or rotationality or irrotational. Then you have learned about the word streamlines. Okay, let me go to the next page. Okay. For example, if you have a cylinder, okay, let's look at a plan view. So you have a cylinder and the flow is happening. So when the flow approaches the cylinder, the streamlines will get closer to each other. Okay. So these kind of pictures you may have seen in your high school books. Okay. Of course, we haven't learned too much about it, but there is some understanding we have about these things. We at least have seen figures like this. Then you have learned about the conservation of mass, or what you used to call the continuity equation. Okay. The area times velocity equal to constant. Whatever flow is entering inside a pipe in 1 second has to leave in 1 second because the fluid is incompressible. The continuity. Learn about Bernoulli's equation, the energy conservation. So Bernoulli's equation, if you remember, is nothing but energy conservation. So it's just a total energy that is conserved. Of course, we're talking about fluids which are inviscid. There's no viscosity in the fluid. And so ideal fluids is what we're talking about. We're talking about ideal fluids is what we're talking about. So the sum of kinetic energy, potential energy, and pressure energy is constant. Okay, so we have an intuition. So if a fluid is flowing at a very fast velocity, then it's got lots of kinetic energy. If somebody throws the water cannons that you see, so they are nothing but they have lots of kinetic energy. They can injure the person. Or pressure energy. if you store liquid or gas at a high pressure in cylinder, if it leaks, it comes out with a very high velocity. So that pressure that is stored in the gas cylinder gets converted to velocity. So high pressure vessels are considered dangerous devices because they have lots of energy in them. So one has to be very careful when dealing with cylinders of oxygen or LPG. And then of course there's potential energy. If I have water which is kept in a tank and it falls from the top, when it comes down with a very high velocity. Okay, so these are energies that can be stored inside fluids. Okay, so this is something we have learned. And then the next thing is we have some very basic ideas about shear stress. This is a bit confusing to many of you, but we still have a very basic idea of shear stress. So an example is that if you have, let's say, you have a surface. So the surface has a normal which is in this direction. That's how it's a flat surface, horizontal surface. So I can apply a force on this surface which is in the horizontal direction along the plane of the surface. So this force that I'm applying, which is along the horizontal plane, is called shear force. Okay. And the idea of shear force comes that if you had, let's say, you had a solid. So you had a solid which was made up of rubber. We're looking at only the front view. So if you apply a force here, then what will happen is this force it's a rubber cube, so it will tend to change the shape. So this kind of a shear force will change the shape of the solid and it will make it into a rhombus. So what we see is that the angle changes. So this square or a cubical solid becomes a rhomboid or a rhombus. Okay, so shear forces tend to change shape rather than changing the volume. As opposed to this, you can also have a normal force. So normal force is a force which acts in the normal direction, that is along the normal or opposite to it, but in the same direction. So this kind of a green or a normal force, we call it Fn, will tend to decrease the volume. If you take a rubber cube and you press it from all sides, it will decrease its volume. It will compress, if it can, of course. I mean, if it's compressible. So this kind of ideas we have. So we have a basic idea about shear force. So let me erase all this. Right. So what we say is that this force which is acting on a plane, the shear force, we can define something called a shear stress, which we denote by tau. That's very typical, and tau is given as this shear force divided by the area of the plane. So if the plane has an area A and the force that is acting is F shear, then we define a shear stress, which is F shear upon area. And this shear stress in fluids will result in the fluid to flow. So what I mean is that if you had, let's say, a volume of fluid which was sitting in a jar, and then you start, well, not in a jar because jar will not allow it to flow. Let's say some sort of a pipe. There was fluid in it, and then what you did was, well, not a pipe, but a channel. Channel is much better. So you had a channel, and on the top you had this plate, a wooden plate that was lying, and then what you did was you started moving the plate. Okay, so the plate started moving. So that movement of the plate on the fluid will result in some sort of a shear on the fluid. So that will result in an F shear. So if that wooden plate which is floating on the surface of some liquid, and you start moving that plate, so that plate will apply some sort of friction or shear on the fluid, and that fluid will also start moving with it. So this tau can now be written as the viscosity mu times du by dy, where u is the x component of velocity and y is the coordinate, which is um, in the direction of well, which is in the direction of the normal of the plane. So this is the normal. Okay. So if you were to look at the velocity profile here, then what you see is um, you see that the velocity on the top is very high because the wooden plate is moving, and the layers just below that are moving slightly slowly until you have zero velocity on the bottom plate, because the bottom plate is not moving at all. So it has to satisfy that condition as well. So you see some sort of velocity distribution. Okay, so this is something we have learnt, and I'm sure you remember those ideas of two discs, and there is some lubricant between them, and the discs are rotating, and so on. So you have done problems like this. So I'll definitely recommend you to, if it's difficult to recall these ideas, please go back and have a look at H.C. Verma's Concepts of Physics, Fluid Mechanics chapter. It's worth doing that. Okay. Right. So this is what we have been doing in school. So let me talk about before I start talking about more ideas for today. Let's talk about the course content. So what are you going to learn in this course in terms of the content? So we will start, of course, with some introduction. We will start with fluid statics, just one lecture on that, and then we'll move to something called integral relations. So what we do is, rather than studying what's happening at those small volumes in the fluid, we talk about the whole fluid together. It is actually much easier to talk about the behavior of the complete fluid rather than talking about individual sections of the fluid. So we will start with that. So we'll spend approximately 6 sessions on integral sessions, and then once we get an idea of how to do this conservation of mass, momentum, and energy on this bulk amount of fluid, uh, which will help us calculate the net force acting on, for example, a pipe, and so on, we will then move to differential relations. Okay, so when we talk about differential relations, you will see a lot of differential equations. So that will remind you of the days when you talk about when you saw those ordinary differential equations and so on. So these differential relations we'll spend a lot of time here. So approximately 8 sessions here. We'll talk about what happens at individual sections in fluid, and then talk about some advanced ideas as to what is the meaning of rotationality and so on inside fluids. Okay, next we'll talk about dimensional ideas or dimensional concepts. It's a very strong tool in mechanics. So rather than knowing the physical idea, sometimes we can come up with some understanding of the relationship between parameters using complete dimensional concepts. For example, if I say quantity A is equal to B, then what that means is the dimension of A has to match with dimension of B. You cannot have a length equal to a time. So on both sides, you have learned this in physics earlier, but we'll use ideas along these lines to talk about to develop relationship between physical parameters in fluids. So this is used to calculate the force acting on a fluid and so on. Then we'll talk about more applied ideas. So then we'll talk about ducts. Okay, so this will again now become a very specific discussion on ducts. And ducts can be of any kind. It can be circular ducts like pipes. It can be rectangular ducts that you see in heating systems and so on. Then we'll talk about flow past immersed bodies. Okay, so that will be 6 sessions. So here we talk about, for example, if I want to calculate the force on a Formula One car, so that is nothing but an immersed body. So that Formula One car is immersed in air as a fluid. So I would want to calculate the forces acting on those immersed bodies. So we learn how the fluids apply shearing or friction on the surfaces. That will be the main discussion session here. Then we'll talk about something called potential flow theory. Okay, so the motivation of this theory comes for calculating the force aerodynamics, basically. So this was developed when people were calculating the forces on airfoils in the aeroplane wings. Okay. Next, we'll spend a couple of lectures on compressible flows. So the idea of Mach number, you know, greater than sound speeds, what happens? There's very interesting phenomena that happens when you start approaching the sound of speed, and it's extremely non-intuitive. I'll give you one quick peek into it. So you have learned about nozzles, right? So you have learned that if you have a nozzle which is like this and the flow is happening from left to right, then what happens is as the flow goes from left to right, its velocity increases. So the velocity at point number 1 will be less than velocity at point number 2 because it's converging. It's like when you have spraying water through a tube, you press the surface of the surface of the tube to decrease its area so that it can increase the speed. But if you go beyond the speed of sound, the idea flips. So if you decrease the area, the velocity decreases. Okay, if the velocity everywhere here is greater than speed of sound. Now this may be extremely non-intuitive, but our intuition is nothing but a function of our experiences. So these kind of ideas are what you will learn in the section on compressible flows. Okay, so 5 lectures on this, and then we'll spend just one lecture each on talking about open channel flows. So for example, flows in rivers and so on. So when the top surface is open, it's free to flow. And then we'll spend one lecture on turbo machinery. Turbo machinery means turbines and so on. So we'll see turbines, pumps. So that's just one lecture because you will have a complete course in mechanical engineering on turbo machinery. It's called energy conversion devices. Okay, so we just want to quickly touch this and show to you that you can use the ideas you have learned in fluid mechanics to improve or to design such devices. So any questions on this? Next is I would recommend that you should stay motivated. So fluid mechanics has been a very interesting field. So I would definitely recommend you to read popular science books. Lots of books have been written in the field of fluid mechanics. So fluid mechanical research has resulted in a significant improvement in research in other fields as well. So for example, I told you about computer science. A lot of research has happened for developing high performance computing machines to help with fluid mechanicists for predicting weather. Again, a lot of work, for example, what Joseph Fourier did in mathematics was motivated from fluid mechanics and heat transfer. So you should definitely read about these things. A lot of work on turbulence or chaos theory has been motivated by the work from meteorologists like Lorentz or fluid mechanicists. And this is still a very open problem that a lot of scientists are trying to solve together. It's a very mainstream field, but it's there in all the fields of research in different departments. So please do read about popular science books, magazines, and there's also movies. There's a very nice movie called Twister. Don't go with the IMDb rating. Okay, do watch the movie if you can. It talks about experimental fluid mechanicists trying to understand how a tornado behaves. So they're trying to put sensors in it and do some streamlines, measurements, and so on. Okay, so very interesting idea. So do stay motivated. That's the whole idea. Right. So now we can go back to our discussion on some fundamental ideas. So we talked about check. So we talked about the idea of continuum concept. That's it. So we'll talk about the second idea for today. The second idea is a theory versus experiment. So theory is, for example, Newton's laws of motion. Okay, so it's a theoretical idea, and it's very elegant. I mean, if you have been able to solve problems in the past, you really enjoy that because of the elegancy of the theory with which it can be applied to real world problems. Okay. So I'll write elegant conservation laws. Of course, there are lots of assumptions involved here. Okay, so for example, in Bernoulli's equation, I assume that there is no viscosity, which is completely, hypothetical. There's no fluid which has no viscosity. Every fluid, the thinnest of the thinnest, has viscosity. Air has viscosity. Okay. So there are lots of assumptions involved in theory. But these can be very good first level calculations in design. So if I'm trying to design an aerofoil, then I can always use the elegant conservation laws and try to come up with the first shape. And then I have to refine that based on some realistic concerns that I have. Okay, so theory is very useful. If I start delving into a new field, then where I have no experience, I can use the theoretical ideas to get some nice estimation of whatever I want to estimate. Next is experiment. So experiments bring in the effect of real world constraints. So if I want to design an aerofoil, what I can do is I can make that aerofoil shape in a lab. And of course, when I say design, I want to design in terms of what is the force acting on the aerofoil when it's flowing with a certain speed. Then I can do experiments on it. Okay, I'll do lots of experiments, and based on those experiments, I will figure out the forces. So I'll make graph like this: okay, force versus speed across the aerofoil, and that will give me some graph that initially the speed is very low, the force is low, it increases, it decreases, and so on. I mean, you can do these experiments for a given shape, so they're very restricted. It's not very general. Theory is very general. It can be applied to a class of problems, but experiments have to be done for particular shape, particular material, and so on. But if I want to get detailed information, then they can be very useful. So what I will see is that the predictions, so if I get graph like this, so when I want to design an airfoil of a larger scale, I can use the scaling ideas, and then I may be able to calculate the force for a given speed, and then that will help me, design an automatic pilot system, because that will tell me that what is the kind of force that will increase. So I have to increase the thrust accordingly to maintain a constant speed, for example. Okay. But the problem is there's no generality. So if a designer has to now change the shape of the aerofoil, they will have to go to the lab again and do lots of experiments. Okay. So both of them have their own plus and minus points. And the reason I talk about these here is that in fluid mechanics, you will see both aspects. So we will start talking about conservation laws, and we'll talk about these elegant theories. And then when we move to ducts, we'll show you that the kind of mismatch we see in the theory and the real world measurement. So then we'll tell you that people, what they have done is, they have done lots of experiments. They have got these experimental graphs, and they have come up with correlations. We call it empirical correlations. So if I get a graph like this of force versus speed, then I will try to fit a graph. So I'll say that it's some sort of linear that fits here, and then we have a cubic polynomial that fits here, and so on. So we will try to fit the force with some mathematical function of u. Okay, so curve fitting is what we'll do. So this is what experimentalists will do, and they'll give you these lots of handbooks with lots of curves like this. And then when you start designing things by yourself, you would go to these curves and try to find out the right kind of force versus force for a given velocity for making your calculations. Okay. So again, an example here would be if you're trying to calculate the drag in a pipe. Okay, so you're trying to design the pumping system for a pipe. So you know that if a liquid, if water flows in a pipe, the surface, the walls of the pipe will create some sort of resistance, and this resistance will result in loss of energy. So you have to have a pump that is connected to feed in the energy that is getting lost because of that friction. Of course, I mean this energy will heat up the liquid, but you have to design, as an engineer, you have to figure out how big the pump has to be so that you can deliver a given volume flow rate at the outlet of the pipe. So if we talk about theory here, then theory will work for different cross sections. It can be circular, it can be square, and so on. It will work for different materials. Okay. So it's basically physics that is applied. So if, for example, you had no experience about pipes at all, you could still apply the theoretical ideas and learn some nice, you predict something interesting. In the experiments, you will always work with a particular cross section. You will have lots of experiments for circular cross section pipes. You'll have lots of experiments for square cross section ducts, and so on, for different aspect ratios on the ducts. So it is cross section specific. Material specific. Okay, you'll do experiments for iron, for different types of iron, for different roughness finishes, and so on. It will also be specific to the environmental conditions in many cases. If you are working in extreme environments. Okay. So this again, experiments is based on data. You generate lots of data, you and then you use that. So it's just like data science or data analytics. So you have lots of data, you analyze that, and you learn something useful out of it. But if you go to a field which is completely new, there's no data available, then you can still use the ideas of theory or physics, and still come up with predictions. So in fluid mechanics, we learn both aspects. And in reality, when you try to solve a problem, the first approach that you have is a physics approach. You tend to attack the problem using your basic understanding of the mechanics, and then you refine further. If you have, if you have given more time to solve the problem, you refine further and improve the ideas based on the handbooks, data, and so on. Okay. So that was idea number 2 for today. Any questions on this? Right. So the idea number 3 for today, which I guess will be the last idea for today's discussion, is called what are fluids? We've been talking about lots of stuff about fluids, but what are they? So we define fluids as those materials which cannot bear a shear stress. Okay. So if you apply shear stress to them, then they will flow. So I'll say cannot well, I shouldn't use this equilibrium. It confuses with net force being 0. Cannot stay static. Under shear load. Okay, so the same shear load. So applying a force on a plane which is in the horizontal direction of plane, so opposite to the normal, perpendicular to the normal of the plane. Okay, so if you have a solid like a rubber cube, you apply a shear force, then the rubber cube will deform, and then it will stay like that. So as long as as long as you're applying that shear force, the solid will be deformed. And when you remove that, if the solid is elastic, it will come back. But if you apply it again, it will still hold. But if you have a fluid, you apply a shear stress, then that or a shear force, that will result in the fluid that will start to flow. So it cannot stay static. It will end up flowing. So what you do is in solids, you relate your shear force as a function of this theta. The more shear force you apply, the more theta deformation you will get. But for fluids, you replace you write the shear force as a function of d theta by dt. Okay. The fluid will keep flowing, so this theta will keep increasing, but there will be fluids for which the rate at which the theta change will be less as compared to others. So in a given second, you will see that some fluids will deform a lot, but fluids which are very viscous, which are very thick like honey, they will the theta change that you will get for them will be much smaller in a given second. Okay, so in fluids we relate the shear force with the rate of change of this theta. Okay, but fluids do take pressure. So if you take of course you know that if there's a submarine that's in the bottom of the ocean, there is a compressive force acting from all sides. So that will compress it. It will try to decrease the volume of the submarine. So they can take compressive force and still stay static, but if you apply a shear load, they'll start to flow. They cannot be static under shear loads. So this is the definition of fluid. Now we also talk about something called an ideal fluid. Okay, so an ideal, well, should put double quotes here. So the word ideal fluid, it means is a fluid which has zero viscosity. Okay, so viscosity again was this shear stress or shear force upon that area is viscosity times uh, du by dy. In fact, it comes from viscosity times d theta by dt. I'll talk about it more in the next lecture when we talk in detail about viscosity. But this relation of mu times du by dy actually comes from this. So this is what we get first from this idea relating shear force to your rate of change of this theta, that is shearing the liquid layer. And from there we can relate d theta by dt is equal to du by dy. Okay, so we will stop here because we are out of time, and I'll continue the discussion next time. So if you have any questions, I'm happy to answer them now. I'll stop the recording.